In this video, we're going to look at composite functions and inverse functions, and in particular focus on the graphs that we've covered, the functions that we've covered since we last looked at composite and inverse functions back in chapter 1. So recall that for composite functions, what we do is we position one function, the output of one function, as the input for another. This is the notation that they've been consistently using in exams. And for a composite function to exist, you need the range of the inner function. So that would be g of x in this case, it's the one inside, or f of x in this case, it's the one inside. We need the range of that inner function, so the values that that function outputs, to be a subset of or equal to the domain of the outer function. So what's allowed to go into f of x. We'll look at inverse relationships, and just remember that if you find the inverse function of an original function, if you compose a function and its inverse, you get x out as a result. And that for an inverse function to exist, the original function needs to be 1 to 1. If its inverse is going to be 1 to 1. So we're going to look at exponential logs and circular functions as well as power functions with fractional powers in terms of composite functions and inverses and things to watch out for with these functions. So let's first of all look at composite functions and exponentials and logs. So with composite functions, be aware that you can solve these if you've got your CAS calculator. Simply define them and then compose them. Often the answer that you get, this is from a past exam paper. This is not the version that was the correct option in the multiple choice section. They'd taken out a common factor of 3 there. So don't expect with composite functions, if you're doing it for multiple choice, for the answer to just pop out straight up. Make sure that if you're working with exponentials and logs and you're doing composite functions, watch out for the inverse relationships in there as well. If you're composing a log inside an exponential or an exponential inside a log function. Also be aware that if you are trying to make a composite function, that you need to be conscious of the domain restriction for logs. You have the same thing with tan. There's a domain restriction for tan. You can't have x values that give asymptotes. And also restrictions for power functions as well. If you have a negative power, if you've got a negative power that you're finding here, then that implies that you're going to have a restricted domain as well. And that restricted domain is that x can't be equal to 0, because for your function x to the power of negative n, it is in fact 1 over x to the n, and you can't have the denominator of your fraction being 0. So this question here is a very interesting question from the 2014 exam 2 for methods. And it's interesting because although it is a multiple choice question, your calculator pretty much doesn't help you with this at all. And so to be able to solve this question, you actually need to know a little bit about composite functions as well as one-to-one functions. So let me step you through how you would go about solving this question. So the outer function that we're going to be working with is in fact a cos function. And so whatever comes out of the log function, whatever the values that come out of the log function, they go in as an input to the cos function. And if we want our function to be a one-to-one function, then what we need is that we need the cos value, cos of whatever we're finding that goes in there, we need that section to be 1 to 1. So let's have a look at our cos graph. So here's a cos graph, and I've used a variable of t so that we don't get confused with a and x from our composite function. And so you can see that our cos of t is clearly not a one-to-one function. It fails the horizontal line test quite spectacularly. But there are sections of that cos graph that we can use that are one-to-one functions. One of which is 0 to pi. So from x is 0 to pi, we have a decreasing function. That's one-to-one if we just took that little section there. We could also take a smaller section. We could go from 0 to pi on 2. We could use this little section here, this domain, and that would also give us a one-to-one function. What that means is our input for this cos function is t. But for our composite function that we're working with, it's not t, it's actually log to the base a of x. So I'm going to start with this first domain here, and I'm going to replace the t with log to the base a of x. And that gives me 0 is less than log to the base a of x is less than pi. Now I can rearrange this so that I have a domain that just has x here. So let's do that by raising each of those values, by putting each of those values as a power of a. And I did that so that we can use this inverse relationship here in the middle to pop the value of x out for us. So a to the 0 is 1 and a to the pi is still a to the pi. So what we've got here is a domain where x is an element of the open domain, so it's not including 1 and it's not including a to the power of 5. And now we've got something that looks like some of our answers up here. It's not any of the answers that we've got, but I've got a to the power of pi here, and there are a to the power of pi on 2s in most of the rest of these answers. And so maybe I need to have a play around with some of these other ones. I've got 0 to pi on 2. So let's have a look what happens with that one if I raise all of those, make those all powers of a. So the middle bit will end up popping out an x like it did before over here. So I'll replace the t with the log, a to the log, it pops out an x. So I'm just going straight to there. And then I'm left with a to the power of pi on 2 for this one. And if I simplify this, I get 1 is less than x is less than a to the pi on 2. And so x is an element of 1 to a to the power of pi on 2. And I'm pretty lucky. That's one of the answers up there, except it's including that 1. So I need to go back and think, can I include that 1 and still have it be a one-to-one function? So if I think about the end points of my interval, the turning point up here, I can include that. If I include that point, it's still going to pass the horizontal line test, and I can include this end point here. So these intervals that I've got here, I could actually have put less than or equal to in both of those situations, and I would have ended up with square brackets here and square brackets here. So the correct answer that I have, or the answer that I have, matches up with C.